Yeah, our goal today is going to be to develop a more general kind of projection. So instead of trying to project a single vector onto a line, I'm going to try to project a single vector onto some kind of subspace. So that's my goal here. I'm going to start assuming that I've got a vector B and a subspace that I want to project onto. Now, the thing is, just to start off, I don't really know what that subspace is, so I'm just going to say some stuff here. So I'm going to say, let's let A1 through AN be a basis for this subspace. So I'm going to call my subspace S, and we'll just say, let A1 through AN be a basis for S. So I'm going to follow basically the same thought I did when I followed projecting onto a vector onto a line. So my first deal is I'm going to write down what does it mean for kind of B parallel to exist, right? So my goal is going to be to have my vector B is going to be a B parallel bit. That's going to be in the subspace S, and a B perpendicular bit. That's going to be perpendicular to the subspace S, right? So B parallel is going to be in S, and B perpendicular is going to be perpendicular to S. Okay, so I'm going to follow this kind of same thought that we did before. So I'm going to write down what it means for B parallel to kind of exist, I guess, right? What does it mean for B parallel to be in that subspace? So if B parallel is in this subspace, that means I can write B parallel as, I don't know, some like coefficients times the basis, right? If it's in the subspace, I can write it out in like coordinates for that basis, right? So I've got x1, that's just some scalar, times a1 plus x2 times a2, and some more of these, and at the end here we'll get to xn an. Okay, so now I'm going to think about this in kind of a funny way. I'm going to think about the matrix multiplication picture with columns, right? So the column matrix multiplication picture would say that I'm making a matrix here with the vectors. So I've got my vectors here in the columns. And then I've got this multiplied by some vector that looks like x1 through xn. For reasons that are not real clear right now, but will become a little bit apparent in the next lesson or the next section. I'm going to write this in kind of a funny way. So I'm going to say I'm thinking about this as a matrix A, that's this dude, and this vector here, I'm going to call X, but I'm going to put a funny little hat on it. There's a reason for that, I promise. It's going to help us later. So what do I know about this? Well, I know that this product is actually just equal to B parallel. Hopefully on board with that. Okay, now what do I know about B parallel? Well, I don't really know that much about B parallel, but I do know something about B perpendicular, right? So I'm going to write down what I know about B perpendicular. Well, I know that B perpendicular is B minus B parallel. So that's first item. Okay. Well, then I wrote down what B parallel was a second ago. So I think I can say that this is B minus A with our X with a little hat guy on it. Okay, and then what do I actually know about B perpendicular? Well, I know it's perpendicular to all of S, which means in particular that it's got to be perpendicular to any of the basis things, right? So I know this. I know B perpendicular dotted with AI. That was supposed to be an I. Come on. Dotted with AI is equal to 0, right? For all I's, right? So for all of my A1 through AN, B perpendicular is perpendicular to those. That gives me a kind of a weird thing that I can write down. So I'm going to write that down in kind of a funny way. So I'm going to write that down like this. I'm going to go ahead and make a box here, And I'm going to be applying this to B perpendicular. So I'm going to make my funny little box here, and I'm going to apply this to B minus AX hat. Right, so this is this guy here. That's just B perpendicular written out kind of a funny way. Now, what am I going to put in here? Well, I'm going to put the A's in here, but because I'm doing this dot product, right, the row multiplication picture would tell me that I'm putting the A's across. And so I'm doing A1 across there, I'm doing A2 across here, going down, I'm doing AN across here at the bottom. Now, I know that the row picture tells me that the dot product, right, of each of these rows with this thing is going to be the components of the resulting vector. That resulting vector in this case, because this is B perpendicular, is going to be 0 for every one of these, right? So I'm going to get the 0 vector out of this. This is just me writing down a condensed version of this previous line where I said B perpendicular dotted with AI is 0 for all the i's, right? Okay, now what is this matrix here? Well, it's not the matrix A, right? It's the matrix A, but where I turned all the rows into columns. If only I had some word for that, right? So that's me saying A transpose times B minus AX hat is equal to the 0 vector. And then I know I can distribute this. So I can say this is A transpose times B minus A transpose A times X hat is equal to the 0 vector. And then I can add this vector to the other side. So I can write down A transpose A done to X hat is A transpose done to B. And then I can use a trick. So the trick is, remember the last video, that A transpose A is invertible if and only if A has linearly independent columns. So here I'm going to apply that trick. I'm going to say, look, A is made out of a basis, right? The columns of A are a basis for the subspace S. That basis, because that's a basis, right? That means that the A's are linearly independent. Because they're linearly independent, I know that A transpose A is invertible. So because it's invertible, I can just invert that matrix to the other side. Be careful. A transpose is not probably invertible, right? A isn't even A probably isn't even square. So A transpose also probably isn't square. So there's nothing you can do about A transpose itself, but the whole thing, A transpose A, is invertible. So that's going to let me write down X hat is A transpose A's inverse applied to A transpose B. That makes sense? It's the whole A transpose A you have to invert. Don't try to simplify this crap. It's not going to work. It's got to be A transpose A that you're inverting, right? You can't invert this bit and then cancel it. It ain't going to work. So this is X hat. Well, nobody asked me about X hat. Where the heck is X hat? Well, X hat was the thing that I multiplied by the matrix A to get B parallel, right? So I can say, all right, so B parallel, the thing I'm kind of interested in here, is equal to A done to A transpose A's inverse done to A transpose of my vector B. Okay, now here's the kick. What I want you to take from this is actually going to be all three of these. Oops, I forgot the third one. Third one is B perpendicular. So B perpendicular is just B minus B parallel, right? So it's going to be B minus A transpose A's inverse, A transpose and B, right? So of these three, I'm going to want you to remember all three of these. So these guys need to go in your head. So insert into brain. And the X hat one is going to be one that we're going to use a lot. The next application here is going to involve us finding that X hat a lot. So I want you to put that one specifically in your head today. The other two are important, but that X hat one bears an outsized bit of importance for us. So I know it seems real silly right now because we didn't really care what that scalar K was when we did the projecting, but now we're going to actually care. I want to jump back one thing quick too. So I want to grab this line and I just want you to look at it. So this line is from the uh this line is from our projecting onto lines. And I just want you to notice how similar this looks, right? This was me writing a formula for W parallel, and here I've got this business. That bears a great deal of resemblance to this guy, except that here I'm allowed to divide by V transpose V. That's because V transpose V was a scalar. In this case, A transpose A isn't a scalar, it's a matrix. So I'm inverting, not dividing by it. And because I'm inverting it, it has to go in this very specific spot in this. So you can't rearrange this formula. It's got to be in the order it's in. And remember, A and A transpose probably aren't invertible by themselves. So if you try to fiddle this around, you can get like this little algebra urge to simplify, and that will screw you up. So don't do it. All right, I think that's what we need for this. Thanks, guys. See you on the next one.